So, okay, the first question is already a transformation question. So, first one, give full details of the geometrical transformation. Represent, okay, the transformation which is represented by this matrix. So 6006. So we know that this is a enlargement, okay, with a scale factor of the 6. But whenever we want to mention like the enlargement, right? So we also need to remember to mention about the origin. Okay, so because the center of the enlargement is at the origin there. So this is what we need to take note. Okay. So part A, the part B, okay, so now we are given a matrix A. So it's a 3, 4, 2, 2. So a triangle DEF, okay, is transformed by A onto the triangle PQR. So given that the area of the triangle DEF is 13 cm square, find the area of the triangle PQR. So what we have for this case here would be, so here the DEF is transformed to PQR by this matrix A here. So when we look at the area of it, so the area of the triangle of the DEF is 13. So we know that the determinant of the matrix will act like a scale factor of the area. So we could find out what is the determinant for the matrix A then. So it gives us a -2. So the area of the PQR is just we have to multiply by the modulus of the A there. So it gives us a 26. Okay, so 1 mark for determinant and another mark for the answer for this area of the PQR here. So the part C is to find the matrix B such that the AB is this 6006. For this one, we need to use the A inverse first. Okay, so we can find out what is the A inverse. So basically for the A inverse is to use the formula, okay, that we can find this A inverse here. So later on, okay, when we want to find the B, right, it is to use the A inverse to multiply by the matrix 6006. Okay, because what happens is that if I've got AB is 6006, so when we just want to find the B, right, we need to multiply the A inverse to both sides from the left. Okay, so that the A inverse A will become an identity times a B. So we only have got the B, which is like an A inverse, and then we've got 6006 there. Okay, so that's how we find the B. So with the A inverse, we can multiply by the B, the 6006 then, and then we just have to evaluate what is the value from here. Okay, so that we get the part C here. So part D. So show that the origin is the only invariant point of the transformation in the xy plane represented by A. So instead of finding the invariant lines that we usually see, right, we want to find now the invariant point. So we want to prove that the origin is the only invariant point. So it's really like we try to solve what is the invariant point, okay? And the answer that we want to see there is just the origin, okay? So we try to find the invariant point. So the invariant point has a property where if we use the matrix to multiply by that point, so the image is the same point. So by using the matrix multiplied by the xy, then it is giving us an xy there. So if you really multiply, we get the two equations there. And then what we need to do is we need to solve from that. So when we try to solve, we are solving the simultaneous here. Basically, by looking at this simultaneous, we sort of already can see that the value of the x and y here is giving us a 0. So really show a bit of the working, okay, to find out that, okay, the x is a 0, and then we could also find out that the y is a 0. So we have solved for the x and y here already, right? So the x and y, it's only taking the value 0. So from there, we could conclude that, okay, the origin is the only invariant point that we have, okay, for a case here, right? So for the next one, so this is the differentiation, okay, for the induction. So the first equation given that is y is equal to x times e power ax. We need to do the induction, okay, so whereby this is the Pn, okay, for the n derivative, we've got the formula there. So first is to prove the Py. So when n is equals to 1, so what we need to do is that we need to find the dy dx. So for the dy dx here, right, it's really about like we do from scratch, okay? Because we know how to differentiate it by using the product rule. So we really do it from scratch. So as we do it from scratch, okay, we can tidy up a little bit. So we get this expression here, ax plus 1 times e power ax. So we write it in this form in order for us to be easier to compare, okay, with the things later on. Okay, so when we compare with the things later on is that, okay, we have to now sub in the n equals to 1 into the result which is given there. So when we sub in the n is equals to 1 and we tidy up a little bit, so it should give us the same as what we did, like we do differentiate it from scratch. Okay, so P1 is true. So with that, okay, we will have the assumption, okay, assume that PK is true whatsoever, the usual thing. Okay, now when we have got the K, the n is equals to K plus 1. So that is, okay, now we are looking at the expression for the K plus 1 derivative. So the K plus 1 derivative means we are going to differentiate the dy dx one more time. Okay, so it's really to differentiate this whole thing, the expression for the dy dx, okay, which is in K. Okay, the n is K now. So for this one, okay, we just have to do a bit of the product rule again. So the only confusing part would be like all the constants A there. Okay, so other than that, it's actually not difficult at all. Okay, because it's the constant A and all the power K that confuse us. But eventually, what we want to do is we want to differentiate with respect to x only. So basically, nothing much from there one. Okay, so for the first time is, okay, we keep the e power ax, we differentiate this whole thing. So when we differentiate this whole thing, we only have got the a power k because this is x, and then this one is a constant, so it will be gone. So another one is we keep the expression for the first one there, and then we differentiate the e power ax, so we get a times the e power ax. So after that is to factorize the e power ax out, and we tidy up a little bit. So after we tidy up a little bit, so we are getting the expression which is in terms of like all the k plus 1s. Okay, so from there we can see that the pk plus 1 is true already. And then after that we will just make the conclusion from there. Okay, the conclusion you can just copy from what is actually asked in the question there. Okay, so let's look at the question 3. Okay, so for question 3, right, the series is given in a long form. So using the method of differences or otherwise show that the Sn is given by this result here. So it might not be easy if you just keep like the term like this. I mean, in the fraction form. Okay, it's not so easy for us to actually look at it. So it would be easier. Okay, it would be easier if we consider like split the terms. Okay, so what we have here is, okay, in the numerator we have got r and r plus 2. So they are the positive long terms. Down here we have got like ln, okay, of the r plus 1 squared. So that would become like ln of the r plus 1 squared, and then we can move the 2 down, so we get a 2 from there. Okay, so that's what we can do, because usually when we want to use the method of differences, right, is we cancel out the terms there. So by writing the expression into everything like this, it allows us to cancel the terms easier. Okay, so with that, we could write down some terms there. Okay, so we will, okay, try to write out first 4 terms and the last 4 terms there. Okay, the reason that we want to do that is because it will show how terms cancels off. Okay, so from here you can see that the terms cancels off in this way. Okay, diagonally like that. So like ln 3 plus ln 3 minus a 2 ln 3 there. So they will cancel off in that way. So if we have already like written down the first 4, we could also list down the last 4 terms there. So everything is easy to see. Okay, everything is easy to see there. So after that, okay, we will just write down, okay, what are the terms that remains. So they are actually all about like the individual long term set that we can combine them together at the end. So this is why we are getting this result. Okay, so we have to split the terms first. So in a part B now, so part B is, okay, we have got the S here. The S, okay, is still the same summation, okay, it's the same sum, But what we have is we want to look at like, okay, the n now approaching infinity. So as the n approaching infinity now, okay, although we have got the ln there, right? Okay, we want to find the s first, yeah. Although we have got the ln there, right? Still, we could work with this fraction here. Okay, so in this fraction here, when we sub the ln in, it will be infinity over infinity again. This is not what we want to see. We want to have the term which looks like a lot of the reciprocals. So both numerator and denominator, the highest power of the n is 1. So it tells us that when we want to evaluate the infinity, we divide by the n, so that we get this expression here inside the ln. So when we have got the infinity, this is 0, this is 0. So we get the s is a ln half. So s here is a specific value. Okay, then only we are using the value of the s here to find that, okay, what is Sn minus s, okay, which is less than 0.01. So we just sub in, okay, Sn and the s, we can combine the terms together. Okay, so this is like ln of n plus 2 over n plus 1. So this one has to be less than 0.01. Okay, so with that, because we are trying to like solve for the c there, right? So basically, it's just to tidy up the things there a little bit. Okay, so you just have to be careful whenever you want to divide something. Okay, whenever you want to divide something there, so just be careful of the plus minus sign there. In this case, okay, what we need to do is that for our e power 0.01 there, okay, especially for this value here, okay, so when we have got the 1 minus e power 0.01, it gives us a negative value for this one, yeah. Okay, so you have to be super careful about it, okay, because it is not so obvious. It is actually a negative value. So when you do the division, when you feel in doubt, then you also have to be careful already. Okay, so when we moved it over, make sure we change the sign here. So basically, this is like the n is greater than 98.5. So the n shouldn't be like decimals, right? So the next n, okay, which is greater than 98.5 is a 99. So this is the least n, because the n must be greater than 98.5. So the first value of the n that we have for that is a 99. So least n value is a 99, because n could be anything which is like more than 98.5. But the least of it must be at least like 99. Okay, so the question will also like help us a little bit, because the question actually asks about the least value, right? So in the case that, let's say you forgot to change the sign here and you get something like n is less than 98.5, then you will feel very weird already, because the n which comes from here, right, is a 98. So because the 98 cannot be the least n here, because we already say here, the n is less than 98.5. So anything which is less than that is fine. So there is no least value of n that gives us that situation here. It is a bit weird in that case, okay? So once we see we have got something like this here, then we might have to check already. Okay, go back to the working and check and see, okay, what happened to that. Okay, so the next question is about the roots. So given that we have got this cubic equation with roots alpha, beta, and gamma, so find the sum of squares of the roots. Okay, this one is the usual stuff that we always do. Okay, very easy is to use the identity here. Okay, this identity is useful all the time. Okay, just type in the correct value and we are getting this already. So the next one is to show that the sum of cubes of the roots is 1. So when we want to find something that has a higher power than the 2, so like 3 onward, usually we will use the essence already, okay? So from the equation, we can write it in the essence form, which is like this, okay? And we want to find the SG here, basically. So we just need to like sum in all the values that we have actually got, okay, in the from the part A there. To sub in, and we're actually able to prove it very easily. It's just a 2 marks question. Okay. So yeah, that's for part B. Okay, part C. Okay, so they sort of like combine the roots question with this. Right. So for this case here, when we want to find the sum of this, okay? The sum of like alpha plus r cube, beta plus r cube, and gamma plus r cube is equals to this whole thing at the right-hand side there. So, okay, what we could actually see from here is that we know that we are going to expand it, okay? We are going to expand it. But as we actually expand it, right, we sort of just need to expand it smartly, okay? We just have to expand it smart. So why do I say that we have to expand it smart is because for each of the cube term there, right, they are actually all the same. I mean, the difference is just about the alpha, beta, and the gamma there. So basically, we just need to expand one of it, okay? So we just need to look at what do we get when we expand this alpha plus the r cube there. So it is giving us like alpha cube plus 3 alpha square r plus 3 alpha, is it 3? Yeah, 3 alpha r square plus r cube like that. Okay, so you are getting this one for the alpha. So for the rest, you can just replace that with the beta and also the gamma only. You don't need to do 3 rounds of the work. Okay, so once we have this expression already, we will notice that, okay, when we add up all the 3 things here, we will get like the sum of the cubes and 3 times the sum of the squares and 3 times the sum of the roots there. Okay, so because each of them, we have got like all the betas and also the gammas, right? And so on lah. So gamma is the same thing. So when you add them up all together, then you will get this result here. So why do they combine it into this is, okay, we are using the previous values to help us to find this one. So sum of cubes, sum of squares, sum of alpha, beta, gamma, everything sub in here, okay? And then only we will reach the steps that we want to evaluate what is this expression in terms of the end there, okay? So we sub in the values of the formula accordingly. Sum of r cubed, sum of r squared, sum of r, and then also we have got the last one is a sum of 1. So the sum of 1 here is actually an n. So we don't need to like really combine the n inside the term there, okay? Just look at the answer first. So the n is actually standalone. So we won't need to make the n inside there, okay? So that we just leave the n alone there, and we just have to deal with like the 3 terms that we have in front here. So before we really factorize the things out, okay, I think it's better for us to tidy up the fractions there first. So we have got like 3/4, 1, and also the 3 here, which we could factorize out the 1/4. Okay, we factorize out the 1/4 as well as those common terms there, n plus 1. The rest of it, okay, these are the remaining terms that we could get from there. Basically, it's just to tidy up and write it into the form that the question wants us to express at last step. Okay. So nowadays they're actually trying to like mix like different types of the question. Right. Okay. So the next part. The curve C, okay, has this polar equation, which is r is equals to 3 plus 2 sine theta. Diagram shows part of C, so sketch the rest of C on the diagram. So this is actually we need to complete, okay, the curve C here. So when we complete the curve C here, it is just like we reflect this part over the y-axis, then we're actually getting the graph there already. Just a 1-mark question, nothing much. Okay, you just want to look at the shape, whether it's symmetrical or not. Okay, so when you sketch, you have to be careful about these this thing here, there's a little bit of the dimple there, okay, because you can see already from the shape earlier. The shape earlier is it has a little bit of the dimple here. So when you actually like complete that, make sure you also make a little bit of the dimple here as well. Okay, so it looks symmetrical like that. Okay, so part B. The straight line L, okay, has a polar equation which is r sine theta is equals to 2. Add L to the diagram in part A, okay, and find the polar coordinates of the point of the intersection of C and L. Okay, so what happened is we have r sine theta is a 2. So r sine theta is a 2 means y is equals to 2. So we just have to add the y is equals to 2 to this diagram here. Okay, because we know that, okay, at this point here, it is actually a y is equals to 5. Okay, so the line which is y is equals to 2 is below this highest point here, which it just has to cut through the graph by two at 2 points there. Okay, so now we're supposed to find the intersection. So starting with the what is that, the equation of the curve. Okay, so we could multiply the whole equation with the sine theta. So left hand side we get the r sine theta because we want to relate it to our intersection point. Okay, so we can have a tool there. So after that is just to solve this quadratic equation. Okay, so for the quadratic equation, we should get two parts for the sine theta. So one part sine theta is a -2, no solution for that. And then when we have got the sine theta is a half, then we can get, okay, the value of the theta here is pi over 6 and 5 pi over 6, which you could sort of like verify it here by looking at the diagram. Then you'll know that, okay, these are the two angles. Okay, you sort of can see that already here. So you verify that, okay, this answer that you get here is sort of correct. Okay, so you also want to find the R value here. Okay, so for the R value here is 3 plus 2 sine theta, right? So we don't need to really sub the theta inside there one because this is a 2 sine theta. We get this theta from the sine theta. So this sine theta will just take the half. Okay, it's easier for us to calculate the value. So no need to sub in the data and then evaluate what is a sine, and then we just calculate from there. Okay, no need, because it's coming from the sine data for the value of the data here. So just sub in the half straight away. Saves us a bit of work. So these are the polar coordinates of the intersection. Okay, so they want the polar coordinates, yeah. So we really need to state at last, okay, what is a polar coordinate, yeah. Okay, and then right. Okay. So the region C is enclosed by the C and L contains the pole. Find the area of R. Okay, giving your answer in the exact form. Okay, so this is a slightly challenging question there. Okay. So they want the region, okay, which is enclosed by the C and the L. So C is the whole heart shape there, and also the L. So means the L will cut the inside the heart shape into two parts. But what they want is the equation that is containing the pole. So the containing the pole is the lower part of this. So they want to have this. Okay. So for this kind of the question, right, we have to be careful and we need to look at how do we look at the area, yeah. So you need to be careful in the sense that we can't just integrate straight away. Okay. So the let's look at what are the values of the data here. The data they give us negative pi to pi. So it is not about integrating from negative pi to the pi. Okay, if we just integrate from negative pi to the pi, it will give us this whole thing, which, okay, this is the thing that we don't want. Okay, this one we don't want. Okay, we don't want that. So when we look at the area here, right, we can think of that as, okay, the area starts from here when it is a negative pi over 2, and it should actually stop somewhere. Okay, it should actually stop at this point here. Okay, so this point here is the point that we have found just now, is theta is equal to pi over 6. So we should stop that, because if we continue to integrate from there, right, it will actually include something that we don't want already from there. So we don't want that to happen. Okay, so for the integration for the area, we will just stop here. We just want to find this part here only first. Okay, so of course the other one is very easy to settle. The other one is to actually look at the triangle. Okay, so it's very easy for us to find the triangle there. So we can find the width and then also the height of the triangle. So the width is basically the x coordinate. Okay, and then the y here is just like the y coordinate of the point P there. Okay, so we just submit x is r cos theta, y is r sin theta. So we have got the r and the theta at that point there already. Okay, so here I'm using the symmetrical property to find, yeah. So I just find the second half here first, then I multiply by 2. Okay, so let's look at the area. So the area here is 2 times. So you can see the big bracket here. There are 2 parts. You can see the second part here is about the triangle. Okay, so this is the area of the triangle then. And okay, after that, what we want to do is we want to integrate. So we get half r squared d theta. Okay, so the r that we have for this one here is that we have got the function r, we square that. So after we actually square that, right, okay, is something that we usually work with. Okay, so again, we will see something like a 4 sine squared theta. So for this, of course, like 4 sine squared theta, we use the identity again. Now, cos 2 theta is equals to 1 minus 2 sine squared theta. We use the identity. And then we will obtain something that is in terms of like a cos 2 theta. And after that, it is not much already. It's all about integrating. Okay. And after we integrate, sum in the limits like pi over 6 and negative pi over 2, sum in everything, and to evaluate carefully from there. So at last, the area is giving us like this kind of the constant. Okay, so it's in terms of the pi as well as like the symmetry as well. Right. Okay. I think this is it, right? Yeah. Okay, next one. Curve sketching. Okay, the curve C has this equation. Find the equation of the asymptotes of the C. So we know that okay, we could do the long division in order for us to get this term. So we can see the denominator x minus 3 that will give us a vertical asymptote. This is x plus 3. Okay, x plus 3 here is our oblique asymptote. Okay, very easy to obtain the two asymptotes here. So for part B, it's also something that is quite typical. Show that there's no point on C for which the y in between 0 to 12. So that is to rearrange the equation such that we get a quadratic in terms of like the x here. Okay, so here because they want to show there is no point. Okay, so we got to use a b squared minus 4ac is less than 0. Okay, so with that, okay, we will get a quadratic inequality. So from the quadratic inequality here, we just need to solve. Okay, then we will get this range of the values of the y there. Okay, so let's look at the next part. So part C is to sketch the C. So for this one, right, okay, what we have, okay, is that we know that, okay, we have got the asymptotes, okay, these two asymptotes here. And for this kind of the graph, we sort of already know, okay, if it is not like this, then it will be like this, the green one here. So because we also found out that in the part B there, there's no value in between like a 0 to the 12 there. So it means that at the 0 and the 12 there, for the y, there must be some turning point. Because this part here is totally blank, nothing there. So it means there should be some turning point somewhere here. So from there, we know that, okay, for the upper part of the curve here, the turning point occurs at the y is equals to 12. And for the lower part here, the turning point, okay, will actually occur at the part where we have got the y is equals to 0. So here they didn't really need us to find what is the exact coordinate of the stationary point here. They just want to see the curve which is like this. Okay, so that's our curve for part C. So in the part D, okay, we have to sketch, okay, the graph which is like the modulus graph, and also the y is equals to modulus x minus 3, stating the coordinates of the intersection with the axis. So this is what they want to see. Okay, so the graph that we need to sketch it is, okay, this part of the curve has to be reflected. So once we reflect it, right, it would also be helpful if we try to reflect what we have here as well. Okay, we can try to reflect it and gives us a guide that we are not going beyond that. So you can see what I actually did here was, okay, I actually really reflected. Okay, I reflected such that when we try to draw, sketch the curve here, right, it doesn't go like beyond, okay, which is what we have here. So it was just still stays within the asymptote step. Okay, so this is the curve that we are getting for the modulus graph there. And then also for another one there is we have got the modulus x minus 3. So this is just a modulus x, but we move down 3 units. Okay, so here's the thing. When we move down 3 units, okay, we have the graph which looks like this. Okay, so here, why do they purposely ask this kind of the thing? Is because they want to see that when we have got the modulus x minus 3, right? So this is the important part. Because when we reflect the asymptotes there, right? Okay, not the asymptotes. Okay, yeah, the asymptotes. Sorry. When we reflect this oblique asymptote, because it is having the gradient of the 1. So when we reflect it, it will actually start from the -3, and then this asymptote is like having the gradient of the -1. Okay, so when we actually have got this modulus x minus 3, right, this line should also have the gradient of like a -1 for this part here. So this is sort of acting like an asymptote. So whereby the graph that we have here cannot cross over it. Okay, it is acting like the row of the asymptote there. So we cannot cross that line. Okay, another part is, okay, this is a -3. And then for this one is that we will also have to show the detail here because it will cross through the x is equals to 3. Okay, the x-intercept is the x is equals to 3, which is nicely our asymptote. So we need to make sure that we cross the asymptote and also this one here nicely here. Okay, so not just simply sketch any line there. Okay, you have to consider like the things which is like on this here. Okay, then you have to be really careful about that. Okay. So in the next part, right, use your sketch to find the set of the values of C, okay, for which this equation has no solution. So what we are looking at in this case is that, okay, no solution means no intersection, okay, or we can look at it as this modulus curve, okay, will be always greater than the modulus x plus c. So you see what I mean, right? So it means if this inequality has no solution, okay, it means that the modulus curve is the modulus of the x squared minus g, x squared over x minus g is greater than that modulus x plus c. Then only this inequality will have no solution. Okay, so the idea is like this. This has no solution means we will have the curve is greater or equals to the modulus x plus the c there. Okay, so from the sketch there, we have to look at like, okay, the graph that we actually sketched there is just helping us already. Okay, so this is the at most, okay, the values of the C at most we can go to the -3. We can't afford to go a bit higher. If you go a bit higher, then they got intersection already. Then they will actually have like solution already. So this is the value of the y that we can go at most. So anything which is lower than that for the curve is no issue. Okay, so there will be no solution to the inequality there. So we want to state that the C cannot go beyond the -3. So it could only go up until the -3. So anything which is less than -3, so we also have the no solution to this inequality here. Okay, think of it in this way, yeah. Right. Okay. Next. So finally is the matrix. Okay. So first is to find equation of the plane OAB, giving your answer in this form, r dot n is equals to p. So basically, okay, what we need to do is we need to recognize that this plane passes through origin A and also the B. So we need to cross the two vectors which are parallel to the plane. So any combination like OA, OB, OA, AB, anything. Okay, so of course the easiest one for us to find here is the OA OB log, because this is like the O, this is like the OA, this is like the OB. Okay, sorry, ABC, OA, OB, and OC. Okay, it's the easiest that we can actually find from there, right? So just cross the OA and the OB there. Then we are getting a multiple of the 1, -1, -1. And for the equation of the plane, it's very straightforward. It's just r dot n is equals to 0. Because this plane passes through origin. So if a plane passes through origin, the right-hand side is surely a 0. Okay? That would be the A. So what about the B? So the B here is, okay, the plane pi has this equation. Find the perpendicular distance of pi from the origin. So you can see this is just a 1-mark question. Okay, so this is to use a very specific knowledge or specific idea, okay, for this distance here is that for a plane, the perpendicular distance from the origin is just we take the right-hand side and we divide by the magnitude of the normal. So the normal of the plane is at 1, -3, -2. We just need to use the 1 to divide by the magnitude of it. So it gives us a distance straight away already. Okay, that's our part B. Okay. Part C, okay, find the acute angle between the planes OAB and also the pi. So this is the angle between the two planes. Basically, it's the angle between the two normal. Okay, so we just take the two normal and then we just have to carry out the steps like what we have in the dot product. So it's the same process throughout. Okay, so I don't need to go through much for this one, I guess. So you can see the last one, okay? Surprisingly, it's a very long question, which is a 10 marks question, and it's the last question of the paper. Find an equation of the common perpendicular to the lines of OC and also the AB. So we need to find out what are the equations for the line of OC and AB first, okay? So OC is very simple. It will pass through the origin, so there's no like point here, is a 0. And then we have got like T times the direction of the OC. Okay, so direction of the line OC, easiest is to take the OC itself, the vector OC. So line AB is different. Okay, we need to work on it a little bit. So for the equation of the line AB, this is the direction of the AB. So it's either we use like B minus A or A minus B. For this point here, you could choose like use like A or point B. It's up to you. Okay, you will get these kind of the equations here. So your working might be a little bit from mine. Okay, but the idea here is, what is a common perpendicular? So the common perpendicular is something like this here. So there are two skew lines, okay? There are two skew lines such that, let's say on the C, we have got a point P, and on the line AB, we have got a point Q, such that this line PQ, right, is perpendicular to both of the lines, OC and also the AB. So this is something that we could relate it back to the skew lines, okay, when we want to find the distance between the two skew lines then. So we need to find the equation of this line. So in which, okay, we need to find the direction of the PQ. So because PQ here is perpendicular to both OC and the AB here, right? So the direction of the PQ here is just, we need to cross the direction from the two lines. Okay, so we need to cross the direction from the two lines there in order for us to actually get the PQ. Okay. Let me just write that down because I'm using an alternative there. So instead, what I actually do for the thing here, okay, is that I am using the vector PQ. Okay, this is like how we do the perpendicular foot in the P3. Okay, something like that. So what happens is that I'm finding the vector PQ. So here, right, we do not know what are the Q and the P yet. So before we know what are they, we will just take the equation which the Q passes through, and then we will just find the equation which the P passes through is, then we minus. So once we minus already, then we will get a vector. So this is a vector of PQ. Okay, so we use the point Q to minus the point P because point Q is on the AB, point P is on the OC. So we use the equations to minus such that we get a vector which joins the 2 points, the PQ there. So we know that this PQ, okay, is we want to find the point P and the point Q. So from there, okay, what are we trying to do from there is that, okay, for this PQ, right, we know that it is perpendicular to the OC. Okay, so for this PQ, we just have to dot it with the direction of the OC there, right? Then we will actually have the 0 because they are perpendicular. Okay, so from there, right? Here we are. So from there, right? Okay, the equation that we will get is this one, okay? 7s plus 27t is equals to 3. So we get one equation from there. So another thing is, okay, we also know that the PQ should be parallel to the AB there, right? So we will have to use the PQ to dot, okay, dot with the direction of the AB. So we get another equation there that we could solve simultaneous equation. So once we solve the simultaneous equation, we will actually get like the either t or s here, okay? So with one of the constant, okay, either s or the t here, substitute it back to the equation of the line. Okay, so once we substitute that to the equation of the line, either the line OC or the line AB, it will give us one of the point. So we just need either the P and the Q here. So it will give us one of the point there, which is in this form. Okay. So after that, what we are going to look at it is, then we know that what is the line PQ already. So the line PQ here is actually given by this point, and then the direction is a 5, -3, 1. Okay, so 5, -3, 1 is actually like we can cross these two, and we can actually get the 5, -3, 1. Okay, I think I did the working here, yes. Okay, so 5, -3, 1. Okay, so there's another method, okay, which I don't really recommend, okay, is it's workable, but it would be more challenging algebraically. So what happens is that, okay, what happened when we actually cross this PQ here? I mean, when we actually cross these two direction of the line here, it will give us the direction of the PQ, okay? Because eventually PQ is perpendicular to both of the lines there, right? So supposingly, when we cross the two directions already, it will give us a vector. So this vector, which is 5, -3, 1, right, should be parallel to the PQ. Okay, it should be parallel to the PQ. So in this case, if we don't want to use the dot product to consider that, right, we could also do the situation where we know that the PQ it should be a multiple of this 5, -3, 1. So from that, you could solve the equation simultaneously, where you equate this one, the PQ here, you equate that with the K times 5, -3, 1. Which is workable, but you have to deal with like 3 variables and 3 equations. Okay, I guess for some of us, we are sort of like quite familiar on how to do that already. Okay, but still it has a very high risk. Okay, for us to actually work on it, it still has a high risk step, because we are still like working with like so many equations here. Okay, so usually I'll just avoid that by working with like the two variables here, by considering the dot product, which might take a little bit more time as well, because we need to deal with like 2 equations here. Okay, it's up to you that how you want to work on it.